In this video, we introduced the limit laws of Calculus 1, and these are the properties of limits that allow us to algebraically evaluate limits for a variety of functions, including polynomial and rational functions and powers and roots of functions. So we'll introduce these limit laws in small batches that make sense to collect together. We'll show examples of how to apply each limit law as we go. And finally, we'll work a couple more examples that combine several limit laws all at once. So we start things out with basically the simplest possible cases. We have the limit of a constant and the limit of x itself. And so if we look at our limit of a constant rule, it looks like a limit of a constant c is just c itself. And to understand why that must be true, we just ask if our function is a constant c, then what does that function get close to as x gets close to a? And because our function is literally equal to c all the time, it's already arbitrarily close to c no matter what x is, no matter what a is. So the limit as x goes to a of a constant c is just c itself. And we can make a similar type of intuitive argument for the limit of x as x goes to a. So this time our function is x, and we're asking what does x get arbitrarily close to as x gets arbitrarily close to a? And I just said it. I just said x gets arbitrarily close to a, so the limit of x as x gets close to a is just a. So these are the simplest of the limit laws, and we can apply them to a couple simple examples. So in the first example, I have the limit of the constant 2 as x goes to 15. And so that function 2 is always arbitrarily close to 2 no matter what x is doing. So the limit as x goes to 15 of 2 is just 2. The next one is the limit of x as x gets close to pi. Just to make it interesting, I threw pi in there, but pi is just a number. So what does x get close to as x gets close to pi? Well, I just said it. It's pi. So next we move on to our first significant limit law. So we can immediately see things are getting a little more complex here. This limit law comes with a preamble telling us the conditions under which this law will be true. And then the limit law itself looks rather complicated. Now what I've done here is actually fold 3 limit laws into one single rule about linear combinations of functions. A linear combination is just a sum of constant multiples of two things. And this idea of linear combinations is absolutely pervasive in mathematics. You're going to see it again and again during your academic career. So I chose to state this first limit law in terms of linear combinations in order to make our list more compact, but also to get some practice thinking about this idea of linear combinations. So if we get into this preamble to our limit law, we're told that f of x and g of x need to be defined for all x on some open interval containing a, but not necessarily at x equals a. And this just guarantees that as we approach a, f of x and g of x are going to be defined at every single point that we sample along the way. But we don't need f of x and g of x to be defined at a in order to find that limit. Next, we create a kind of shorthand for the limit of f of x as x goes to a and the limit of g of x as x goes to a. So we're going to say L is the limit of f of x and M is the limit of g of x. And this just allows us to state our limit laws in a little more compact notation. Finally, we're told that c and d are constants, in other words, just some real numbers. And there's our limit law. The limit of a linear combination of two functions, that's a sum of constant multiples of two functions, is equal to the linear combination of the limits of the functions. So I start out with the linear combination c times f plus d times g. I apply the limit to that and I get c times the limit of f plus d times the limit of g. And the shorthand notation for that is cl plus dm. Now in every textbook I've seen, this is actually stated as 3 separate laws. And I want to show how this idea of a linear combination can give you those 3 different rules, just doing it all in one rule. So all we have to do to get the limit law for the sum of two functions is say let c equal d equal 1. And this gives us the limit as x goes to a of f of x plus g of x. And applying our rule about linear combinations, this is going to be c times the limit of f, but c is 1. So I end up with the limit of f of x as x goes to a plus d times the limit of g, but again, d is equal to 1. And we conclude that the limit of a sum of two functions is the sum of the limits of those functions. So this is just a special case of the linear combination rule. Now, if we want to rule for a difference of two functions, we just cleverly pick our c and d to make that happen. So I'm going to say let c equal 1 and let d equal -1. This gives us the limit as x goes to a of f of x minus g of x. And using our rule for linear combinations, we get c times the limit of f, but c is equal to 1, plus d times the limit of g, but d is negative 1. So I have minus the limit as x goes to a of g of x. All right, so the linear combination rule just gave us a rule for differences also. Finally, we can say let d equal 0, and we end up with a rule for constant multiples. So I have the limit as x goes to a of c f of x, because I already let d equal 0. That's going to be equal to c times the limit as x goes to a of f of x, plus d times the limit of g. But I said d is 0, so that term vanishes. So we have our rule for constant multiples. So just be aware, if you look in a typical textbook, you'll see 3 different rules, and all these are saying is really one thing. Limits respect linear combinations. So here's a quick example illustrating how to apply this rule. In this example, I have the limit as x goes to 4 of 3 minus 2x. There probably should be parentheses around that. And I see a linear combination of 2 functions. One of them is a constant function, and then I have minus 2 times another function, which is just x. And we know how to find the limit of a constant or x. So we're going to apply the linear combination rule and say this is the limit as x goes to 4 of the constant function 3. And then I have minus 2 times the limit as x goes to 4 of x. So we've broken this down into 2 limits that we already know the rules for. We have a limit of a constant 3, and that's just equal to 3, no matter what the x value is approaching. And then I have minus 2 times the limit of x as x goes to 4. And again, as x approaches 4, x gets close to 4. And now I have 3 minus 8, or negative 5, for the value of that limit. Now our next limit laws concern products and quotients. And note that the preamble is the same here. We're talking about the same context. I have a limit of f of x that we call L and a limit of g of x that we call M. And these have to be defined on some open interval containing A. So the first rule is for products. And again, it's not much of a surprise. The limit of a product of 2 functions is equal to the product of the limits of the individual functions. And our shorthand for that is L times M, where L is the limit of f and M is the limit of g. The rule for quotients is again unsurprising. The limit of a quotient of 2 functions is the quotient of the limits of those 2 functions. So the limit of f over g turns out to be L over M. But I do have to throw in something extra here. I have to indicate that this isn't going to work if M is equal to 0, because that would cause division by 0, in other words, an undefined expression. So our quotient rule is only going to work if we have a non-vanishing denominator. So again, I want to emphasize that this was the simplest possible way limits could behave. A limit of a product is the product of the limits. A limit of the quotient is the quotient of the limits. Watch out for 0 denominators. That's it. So to apply this to a couple simple examples, in the first one, I have the limit as x goes to negative 1 of x times the quantity x plus 5. So that's a product of 2 functions. The first one is x, so I can write this as the limit as x goes to negative 1 of x. And I'm going to multiply that by the limit of x plus 5 as x goes to negative 1. All right, so the limit of a product is the product of the limits. And now I know how to evaluate that first one. The limit of x as x goes to negative 1 is just negative 1. And then the second one, if I'm being extremely careful about going step by step with the limit laws here, the next one is a linear combination of 2 functions. It's a sum of 2 functions. One of them is x and one of them is 5. So I can break this down as the limit as x goes to negative 1 of x plus the limit as x goes to negative 1 of 5, because limits respect linear combinations. And we know the rule for each of those. I'm going to carry the negative 1 over here. The limit of x as x goes to negative 1 is just negative 1. And the limit of 5 as x goes to negative 1 is just 5. So I end up with a negative 1 plus 5 in those parentheses. And cleaning things up, inside the parentheses, that's 4, and I'm multiplying it by negative 1. So the value of this limit is negative 4. In the next example, we have a quotient of 2 simpler functions. So I have the limit as x goes to 2 of x divided by x minus 3. So what the quotient rule says is this just breaks up into a limit as x goes to 2 of x. In other words, the limit of the numerator divided by the limit of the denominator. Limit as x goes to 2 of x minus 3. And again, we'll try to be as rigorously step by step using the limit laws as we can possibly be. In my numerator, I have the limit of x as x goes to 2, which is just 2. And in my denominator, I have a linear combination of 2 functions. The first one is x and the next one is 3. So I have the limit as x goes to 2 of x minus the limit as x goes to 2 of 3. Note that it's completely equivalent if I wrote a plus in between these two and I just called the constant -3 instead. We're going to get the same thing. It's a -3. So simplifying in the denominator, I have the limit of x as x goes to 2, which is 2, minus the limit of 3, which is just 3. And I end up with a 2 over -1, which then simplifies to -2. Finally, we get limit laws for powers and roots. And these are stated in terms of integer powers and integer roots, but we could extend these to including any real exponent. And again, there are no surprises. The limit as x goes to a of f of x all raised to a power is the same as taking the limit of f of x first and then raising the result to the power of n. The shorthand for that is L to the n, and we're told n is going to be an integer, at least for now. And the same is true for taking the nth root of a function. So the limit of the nth root of f of x is the nth root of the limit of f of x, or the nth root of L in our shorthand notation. And we do need to note there that if n is an even number and L is negative, then that root is not going to be a real number. So we want to exclude that case. So we're told if n is even, this is only going to be true if our limit L is greater than or equal to 0. So there's our powers and roots limit law. Again, no surprises there. The limit of a power is the power of the limit. The limit of a root is the root of the limit. So here's a couple of quick examples. In the first one, I have a sum of two functions to start with. And so I'm going to break that up using the linear combination law. So the limit of x to the 5th plus 7 is going to be the limit of x to the 5th plus the limit of 7. And then we can do each of these pieces individually. And that first piece requires the power rule. So I have the limit of x raised to the 5th power. That's going to be the same as the limit of x, taking the limit first, all raised to the 5th power. And we'll go ahead and clean up the limit of 7 right now. The limit of 7 is just 7 no matter what x is going to. And again, I know how to compute the limit of x as x approaches 2. That's 2. So I end up with 2 to the 5th plus 7. 2 to the 5th is 32. So I have 32 plus 7, which is 39. And we're done with that one. The next one is an integer root. I have the limit of the cubed root of x as x goes to -8. And what this limit law on roots tells us is that we can just take the cubed root of the limit as x goes to -8. And now again, we have a rule for computing the limit of x as x goes to a number. As x approaches -8, x gets close to -8. So I end up with the cubed root of -8. That means the number that I raised to the 3rd power to get -8, and that's -2. And we're done with that one. Now to wrap things up, we're going to show a couple more examples where we have to combine a bunch of different limit laws and be very careful about mentioning at every single step what limit laws we're using. So what I like to do in my classes is actually make a numbered list of the limit laws just for the sake of compactness. And then I'll have the students tell me what number law they used at every step in the simplification. Before we get into the examples, I want to summarize the main point first. And the main point is that limits behave in the simplest possible way with respect to linear combinations, products and quotients, powers, and roots. There are absolutely no surprises in the limit laws at this point. So they should be very easy to remember. The limit of a linear combination is the linear combination of the limits. The limit of a product is the product of the limits, and so on. So here's our first example. And what we're asked to do here is evaluate this limit, being extremely careful to apply one limit law at a time and noting which law we're applying. So the way I need to start on this rational function is to just say, okay, the limit of a quotient is the quotient of the limits. So I'm going to break it down to the limit of the top divided by the limit of the bottom. Okay, so that one's done, but we should probably make a note of what limit law we used. So I'm just going to say it like this. I'll just say quotient law to communicate what limit law I was using there. And now we have a linear combination in the numerator and a linear combination in the denominator. So framing the limit laws in terms of linear combinations is just so much simpler because I can say the limit of a linear combination is the linear combination of the limits. I don't have to mention a constant multiple rule and a sum rule and a difference rule all separately. Okay, so the numerator breaks up like that, just using the fact that limits respect linear combinations, and the denominator breaks up like that. And we'll just make a little note that we use the linear combination law to get that done. Now we're almost ready to evaluate all of these pieces using our first two limit laws about the limit of a constant and the limit of x itself, but we still have this one problematic limit. We have the limit of x cubed, so the limit of a power, and that needs to be written as a power of the limit of x. So that's all we have to do there. The limit of x to a power is the limit of x then raised to a power. And we make a little note that what we used there was our power law. And finally, we've broken it down to either limits of constants or limits of x itself. And so we go back to those first two basic rules and start evaluating this thing. In my first term, I have the limit of x as x goes to 1, and that's just 1. So I end up with a 1 cubed. I'll just keep it that way for now to make it more clear where it came from. In the next one, I have minus 4 times the limit of x as x goes to 1. So I'll write that as negative 4 times 1. In my third term in the numerator, I have the limit of 5 as x goes to 1, which is just 5. In my denominator, I have 5 times the limit of x as x goes to 1, which is 1. So I have 5 times 1 there, plus the limit of 2 as x goes to 1, and that's just a 2. Now cleaning things up, I have 1 minus 4 plus 5, which is 2 in the numerator, and then 5 times 1 plus 2, which is 7 in the denominator, and we're done. In our final example, we have a product of two pieces, and one of them is a square root, so we have a chance to use our root law. So we begin this one by breaking it up into factors. So the limit of a product is the product of the limits. Again, there are never any surprises with these. So I have the limit as x goes to 4 of x squared minus 5, then multiplied by the limit as x goes to 4 of the square root of x minus 3. And we'll just make a little note that we use the product law for that. Then in the first piece, I have a linear combination of two functions. So I can write this as the limit as x goes to 4 of x squared. Again, we're trying to not do too much at once. We want to identify explicitly what law we're using at each step. So I have the limit as x goes to 4 of x squared minus the limit as x goes to 4 of 5. And again, it's perfectly valid if you wanted to call that plus the limit as x goes to 4 of negative 5. You're going to get the same thing. Now I'll go ahead and go out on a limb here and just apply two limit laws simultaneously and just make a note of it. So that was the linear combination law for the first piece, and then I'll use the root law for the second piece. So I end up with the square root of the limit as x goes to 4 of x minus 3. So there's the linear combination law, and there's the root law. All right, so we continue. In our first piece, we have a limit of x squared, which we need to use the power law on. So I have the limit of x squared, which is just the limit of x, and then square the result. And then inside of our square root, we have a linear combination. So we'll use the linear combination law on that. And I end up with the limit as x goes to 4 of x minus the limit as x goes to 4 of 3. So at this point, it's broken down into limits of x and limits of constants. I'll make a note real quick on what rules we used at that step. And now we can finally use those two simple limits. The limit of x as x goes to 4, that's just 4. And I have to square that. Minus the limit of 5 as x goes to 4, so I have a minus 5 there. And then I have the square root of the limit of x as x goes to 4, which is just 4. And then minus the limit of 3, which is just 3. So 4 minus 3 is 1, and the square root of 1 is just 1. So that piece is just 1. And I'm left with 4 squared minus 5. That's 16 minus 5, which gives me 11, and we're done with that one. Now those last two examples were undeniably cumbersome. And you might be saying to yourself, wait a minute. If I go back to this first one, this rational function, we went through all this stuff, but isn't it just totally equivalent to replacing x with 1 in the expression I'm taking the limit of? So if I just look at this rational function and replace all the x's with 1s, I get precisely this expression that we got at the end of applying all those limit laws. And this is because the limit laws behave in the simplest possible way. You'll see the same thing occur in our second big example. By the time we cooked it down to that final expression where we evaluated all the limits, it's equivalent to just replacing all the x's with 4s. So the reason this ended up in the calculus curriculum is that we want to give students a taste of being just a little more rigorous in justifying their logic as we go through applying the properties of limits. And it is true that these both come down to just replacing x with the value that it's getting close to in the limit. And we can prove that it works that way and then use that property in the future to just shortcut all of this statement of limit laws. That's the topic of the next video, and I'll post a link to that at the upper left, and I'll see you there.